Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this thing seems to be working. Good. We are happy. We are happy to have Gabor. Is it Pete or Pete or Pete here from UC Berkeley? He's a postdoc candidate, and he is going to be talking about corner percolation on Z2 and the square root of 17.
Okay. Thank you for the invitation. Okay, so the model. This is scary. So I'm going to talk about this model. So a random subgraph of Z2, and where you might find out how to define it from the picture. So what we want is that at each vertex, we want to see exactly one of the four possible corners, namely, so the two incident edges which are perpendicular to each other. So this looks like a local conditioning. So otherwise, we want the maximum possible randomness. So we want to define a random subgraph with this corner condition. And so this was a model.
Latsi Levas has built a terrace with that pattern on it.
He didn't do it randomly, required to have one pass leaving one door
Entering another. It was just commenting that that's Latsi's
That's the
terrace.
same rule. On each tile you have two entry points which are interacting.
Anyway, go on.
Okay, so the model is due to Balint Toth. Okay, so although it looks like a local conditioning, it's very easy to see that actually it forces a infinite range dependence. So on each infinite vertical and each infinite horizontal line, you have to have every second edge in and every second edge out. Just because you can see. So if you want to define the most random maximal entropy or something measured on this subgraph, then so basically the only choice you have left with is to decide for each line, for each infinite line, if you keep the odd or if you keep the even edges along that line. So I flip a fair coin for each infinite line, and if I see odd or even, just plot it one half each independently. If I see odd, I keep every odd and keep every even. So that's the model. Clear? Okay, so just by deterministically, so it's a two regular graph, subgraph of Z2, which means that the components are either finite cycles or by infinite paths. So these are the two possibilities we can have. And what Balint conjectured is that we have only finite cycles. And so this is theorem 1, that we almost surely we have only finite cycles, don't have infinite components. Moreover, every point in the plane is surrounded by infinitely many cycles. And so why is this that one should expect? So this is like a linear entropy brother of several like classical conformal invariant processes, if you want. So one is that, well, it's critical Bernoulli 1/2 percolation. You just have this locally looking conditioning, the corner condition. So hopefully it has only finite, but kind of big components. A bit more, yeah, I said naive reasons. A bit more convincing is.
So when you say that they're finite components, but they're infinite expected size components
Yes.
in the same way as the naive reasoning from Bernoulli percolation. I mean,
Yeah, like the
Right.
they're kind of big.
yeah.
Of course, the critical exponents are different. So, I mean, the details of the critical behavior is not preserved by this insane conditioning. Yes, a little bit more convincing is connection to the double domino model, which is you take a 2n by 2n box, and you take a perfect matching. So you take all possible perfect matchings on the domino tilings on the 2n by 2n box, and you take one of them uniformly at random, and you take another one independently, and you put them together. So can you see? So the green edges here are the green dominoes, and the red edges are the red dominoes. So when you put them together, you get a two regular graph. And as n goes to infinity, this has a weak limit. So this is somehow the. So basically, this I could call the most random measure on Z2 with the condition on each vertex to have degree exactly 2.
Why do you call it the most random?
It's the maximal entropy measure on these things. But this has actually quadratic entropy, so maximal entropy in the planar sense. Okay, so our model is like you take one tiling consisting only of vertical dominoes and one tiling consisting only of horizontal dominoes, and then you put them together. And here it is true. It's Scott's thesis, and so these people did it in different versions. They prove that they have you have only finite cycles, and each point is surrounded by infinitely many cycles. Okay, but the point but the methods here don't work at all for our model, because like proving that this has only finite cycles, you use things like finite energy conditions, so Gibbsianity, things like that, which we don't have here at all. So those things won't work. Okay, and the third pretty well-known two-dimensional model is simple random walk. Okay, let's see. So instead of simple random walk, I will use almost simple random walk, which means that on odd steps you have to move horizontally, and at even steps you have to move vertically. So this scales to Brownian motion still. And so our walk has some big long-term memory. The way that so basically you have to decide in advance for each horizontal line and each vertical line which direction you will go on that line. And then when you start walking, so the first step is vertical, and the second step is horizontal, the third step is vertical. And once you have taken one direction on a line, you have to keep that direction. Whenever you visit that line, you have to keep that direction. So if you walk with this rule, then the trajectory you get is exactly the component of the origin in the corner percolation configuration. Clear? Okay, and so almost simple random walk is recurrent. So this is a two-dimensional walk. It should also be recurrent, which in our case it would mean that it doesn't go off to infinity, but comes back to the beginning. Okay, so to show how, I mean, this is a possible explanation, but to see how weak the explanation is, that you interpolate between almost simple random walk and our random walk by doing the memory thing in one coordinate and simple random walk in the other coordinate. So the easiest way to do this, so you take z, once and forever you fix Bernoulli 1/2, so plus minus signs on z, and then you start a random walk from the origin. So this is this red thing is a simple random walk, and whenever you step into a vertex, you add this sign into your bag. That will be your horizontal, your vertical coordinate. So your horizontal coordinate is the simple random walk, and your vertical is this sum in your bag. And you, so this is, so corresponding to this simple random walk, this is the complete walk. And you ask, does it happen that you add back to the origin in the walk, and the sum in your bag is 0? So this is exactly between our model and almost simple random walk. These are two recurrent. Well, I will show that our walk is recurrent, simple random walk is recurrent. So, but this interpolation is transient, which is homework. So you can kind of easily see that.
The 5/4 you're saying is easy? Or?
Yes. So you just try to see it. So yeah.
Okay, that's not a deep 5/4.
No.
That's like not a.
No.
Yeah, okay.
No. Actually, these people wrote a paper on it. Well, I mean, they also gave like I'm not sure if the exact log correction, but there is some. Okay. Okay, so this is like a long-range dependent thing. And usually, I think this is considered hard. At least my advisor, Yuval Perez, told me off for doing this problem. So he said that, oh no, this is not solvable. Don't do it. Okay. A different approach is to...
So you went against his advice?
Yes.
Good stuff.
Okay, so... And the reason for going against the advice is that you start drawing some figures. So you want to understand how these... So if there are only finite cycles, then, well, look how the finite cycles look like. So you start drawing them. Sorry. I have drawn too many in my life. No, I cannot do it. So this is like one cycle. And you draw some bigger ones. So this is of length 18,000. Okay, and so this is one cycle. So there is a connection here. And you see some obvious symmetry, which is that if you take the smallest enclosing rectangle, then the points where the cycle touches the sides of the rectangle, so this point seems to be at the same place at this touching point, and this touching point is at the same place as that touching point, and this kind of happens on all scales, like smaller, kind of happens. Okay, so this is a statement, and also you can add to the statement that this line, the connecting segment between, is inside the cycle. So the cycle doesn't cross in the connecting thing. Okay, so this is a combinatorial statement. It has nothing to do with randomness. I claim that however you draw a cycle with this rule, it will have this property about touchings. And if you want to prove it, then, well, it's a finite statement. You prove it by induction. So if it is true, what happened to the slide? Okay. So if it is true, then do we have a? No, never mind. Yeah, never mind. Not that.
Well, you can point on that.
That's true.
Or your, I mean, it sees everything now. It doesn't just see the reflection. Like if it nails your
Yeah, I know.
it sees it.
So if it is true that these touching things happen at the same point, then it's also true that the signs. So this, if this, yeah, that's not very good. So this sign, if this is odd, then this also has to be odd. Clear? And also, I mean, obviously, wherever it touches the side, these two. Thanks.
Big brother.
Yeah. I see. Okay. So those, well, there is a matching. Sorry, this is just easier. So there is a matching. These two signs are the same. Okay. That's all I want to say. Okay, so if you want to.
You're saying wherever it touches, the signs have to be the same.
Yes, I mean,
Yeah,
this sign has to be the same as this sign. That's all what I. Okay, but of course it doesn't have to be this odd doesn't have to agree with that odd or that odd. With that odd or that odd. Okay, so if you want to prove the statement by induction, then you can try to delete something from this figure and hope that what you get, a smaller picture, has some resemblance, and you can apply the induction hypothesis to that and get back something. So what you have to delete, so this is some experiment that you have to make what you have to delete. So if you really delete the outermost two signs and the innermost two signs, oh no, actually, so if you delete the outermost two signs there, then in the other marginal configuration you have to delete the innermost signs. So if you do this operation, then although this big cycle breaks up into smaller cycles, usually.
Wait, so you just delete two, though? You don't
You delete everywhere where it touches the.
Oh, everywhere where it touches. Okay.
Yeah. Yeah. So say you delete these 6 things and those 2.
Okay.
And you just push the
Okay.
figure so that you get an actual, the product of 2 marginals. Okay, so the cycle breaks up into smaller cycles, but you can control, kind of they fill up the rectangle, and you can control that after you put back the all signs, how they get connected to one cycle. So there is an intricate.
So what exactly do you remove, and how do you, when you remove some edges, then it becomes disconnected, not the cycle even?
Right. It's like 3 cycles now, I think.
So maybe you can see the cycle there. And there are these corridors. So these are the 2 touching points. And the claim was that also the connecting segment is contained completely inside. So those I call corridors. So you delete. So here I deleted, okay, so there are 2 touch points there. So I delete those 4 signs, and I delete these 2 outermost signs in the. So in the horizontal marginal, you delete the places where the cycle touches the.
So those black rows and columns are what you delete?
So here I delete this 1, 2, 3, 4 signs from the configuration.
The minuses that the pattern is bad.
So auto easy.
if you have something like that, and okay, so wherever the cycle touches the rectangle, you have to see the same two signs. And when you delete them, you just get, so you delete this part of the picture, meaning that you get plus, minus, plus, plus, minus. And you do it everywhere where the cycle touches the rectangle, horizontally. And vertically, you delete the two outermost signs. So the whole thing, so it's smaller by 2 this way, and it's smaller by 4 horizontally in this picture.
But if you're deleting like the two outermost, so on the top, it's always going to be 2 on the top, but it could be like 10 on the other side. This just
sure.
happens to
Yes,
be
whatever.
But it would always be 4 on the top if you're deleting.
No. You always delete all the touching places.
All the touching places, okay. Not just the outermost.
Yes, no.
But by outermost,
No.
you mean touching places.
No, by outer, so horizontally, you delete all the touching places. Vertically, you delete the two outermost signs.
So why do you then have the second line going through?
This line,
Yes.
this just shows that there is also a horizontal corridor. In the construction,
I see it's not about which one.
yeah. Okay, and what you get, so this original cycle broke up into smaller cycles. But you can try to apply the induction hypothesis to these smaller cycles, saying that, okay, we have some touchings here, and so on, and see how they get glued together when you put the thing back. Okay, so when you repeat this induction step until you get to the empty cycle, you realize that there is some structure to the signs in the marginal, which is that there is I don't know what is that. Okay, you see? Okay. So there is a natural matching between the signs in the marginals. So the matching is non-crossing, and you match even signs with even signs and odd signs with odd signs. And it could happen that, if you have some configuration, then like odd, sorry, the plus minus are odd even. If you like odd, then this is one possible non-crossing matching, and this is another possible non-crossing matching. You want to choose the one for which the total length of the bridges is as small as possible. Okay, so this one. Okay, and somehow, so that's a statement that whenever you have a cycle, in the marginals, the signs you see in the marginal, those are matchable. So there is a non-crossing matching this way, and somehow this optimal matching somehow corresponds to this structure you see. So somehow the cycle is the product of these two matchings, and this matching is also, it looks like a simple random walk excursion. So if you just count the number of bridges going over a place, that's a simple random walk excursion trajectory. So it's also the same as if you have probability 1/2 closing and ending brackets, and you want to find the smallest, the first place which is meaningful bracketing. So this is a simple random walk excursion.
You're just going to say that the height doesn't get that big, and by the time you've done it, you can collapse it too.
Yeah.
That's a nice.
Now I have a question there. So if you look at this random walk, it has sort of, it seems, so in this matching I can think of sort of, there's also a partial order between matchings, namely things that bracket each other. And it seems that the innermost in this bracketing always correspond to the local maximum.
Yes.
In your,
Yes. It does.
both in your walk and also in the curves.
Okay. Yeah. So once you, so this is a statement you can prove with induction, and once you have done that, you can realize that there is a very nice way to generate the whole corner percolation thing using simple random walks.
If you multiply the alternate things by plus minus, I mean, so instead of odd even, you just multiply. Is it true that between 2 points where it meets, the number of odds will be equal number of evens? Not in this notation, but if you just flip the alternate.
Yeah. So what? Yeah. So you have to. So if these are plus minus ones, and you every second you flip, then what you get is then this is exactly this simple random walk trajectory. So the increments for a simple random walk trajectory. So you see if, like this thing if so in the original, so if it was odd, even, odd, so the matching is this. So you flip every second one, say odd is plus, so this is minus, then, sorry, this. Okay, so originally this is the thing. Okay, now you flip every second one. So this becomes plus, and this becomes minus. Now you look at the simple random walk that it gives. So plus, minus, minus. Okay, so this is the height here is the number of bridges over there.
With the condition about minimizing the total lengths of the bridges that you gave, right? When you had DEEE, you have two choices, but only one's valid.
Yes, only so that choice is what actually makes it. Okay, no. So somehow this. So here. So this corresponds to this simple random walk. So somehow this is not an excursion, but it has, like it's actually two excursions next to each other.
Is the valid one or the invalid one?
So you want to use the top one,
Yeah, right. Yeah.
and this is not an excursion. This is two excursions, which means that actually whenever you see so the statement implies that whenever you see a cycle, then in the marginal you won't see this configuration, because you will see, that's what I claim, that you will see exactly an excursion.
But you won't return.
But it's
to the-
invalid.
You won't return, so you won't have,
when
so
you
this
return,
thing,
the cycle breaks.
yes. So if it had returned, the cycle
Yeah, right.
would have
It
been
broke
smaller.
into two cycles.
But that was a condition about the little inner part, right? The very innermost thing, wasn't
Well, so these are the maxima,
it? They're like up there.
and the minima cannot be 0.
Right, yeah.
They have to be positive.
And I thought you were imposing a maximum on see the leftmost, the ones that are on the leftmost boundary. Now the leftmost
Up.
boundary of the cycle. The leftmost boundary of the cycle.
Leftmost boundary,
so
yeah,
you
these
say
ones.
Those six,
You
yeah.
said that you can't choose the other bracketing there. You cannot choose.
No, you don't want to choose. I mean, it's,
that would correspond to a walk, though, wouldn't it?
But his
No, it wouldn't.
correspondence
Then the
between
correspondence-
bracketing and the cycles is choosing that top one, not the bottom one.
Oh, but what
Yes.
if you
He
had
says never
that
choose
walk?
the bottom one. That's
What if you had that walk?
Or
Would
the
you have
different
an
map.
excursion there?
the difference.
if you had,
Different mapping?
So what if you had that walk? So
Yeah, I thought
what,
that
what
you choose the-
curve on the right, if on the left, okay,
the same-
when you
it's the same
point
walk.
to the 000,
yes.
on the left, the walk has a little dip. So go
Okay,
up
this,
to the-
yeah.
Now go to the left. To the left of your picture.
On the purple
The
one.
walk has a dip.
The
Okay,
walk,
there's a
yeah.
walk has a dip.
Yes.
What
It
if
does.
that dip went outwards? How would the curve look?
There will be two even signs here,
what
and
if
the
they
curve
go
would go more out.
Further out.
Further out.
out? Leaves the box.
Yes. Mm. Hmm?
So you have to choose that one to have
Yes.
correspond to your cycle.
Yes, yes,
Oh, but we
yes.
don't- we don't
I'm just saying
That
that.
one choose, yeah.
Mhm.
But now you've mapped it into this simple extrusion, which
Yes.
is much easier to deal with.
Yes,
Yeah.
yeah. So yeah, this odd even I will. Okay, so the easy description is that you take two two simple random walks on Z. So this is xn and ym. Okay, so time is by infinite for both things. So one is the vertical walk, the other is the horizontal walk. So these are the heights.
Wait, is your walk floating or does it at time 0? It's in position 0? What?
Say 0 at time 0. Okay, and then you define this height function on the faces. Okay, so the coordinates correspond to faces of the lattice. So you define a height function on the faces of the square lattice. So by this rule, so you add up the two random walks, divide by 2, take the upper integer part. So this 3 comes from this 1 and this 4, 5, 2 upper integer part. So you get a height function on the faces, and then you take the level separating lines. So you draw an edge if the two faces don't have the same height. Okay, claim, which is obvious, that you get a corner percolation configuration. You can kind of see, just by parity, and so by parity, you can easily see that every second edge has to be in, and just by the independent increments of simple random walk, it has. You can easily see that whether it's the even or the odd edges on neighboring lines, those are independent. What you want to have.
The same would be true if you took the lower integer.
Yeah, sure. It's just one. It's just a normalization.
What he's done is off.
Uh,
No. Oh, sure. Have you shown this to physicists or not? Because, even the physicists, I think, would kind of,
Like Denis or...
people like that, I think, would really go for this.
Mhm.
Because it's kind of it's something, it's a nice mapping. It's a very nice
Mhm.
mapping.
no, I haven't. Okay. So we have this height function on the plane, and we have these contours. So the contours are exactly the corner percolation. It's exactly a corner percolation configuration. Moreover, the heights themselves make sense. So when you have your corner percolation configuration, there is a natural height function. So if you look at it as a contours in a map, you can define a height function. Now, in a map, if you have height a lot, you know that sometimes it's a problem that you don't know if that's a hill or a valley that you see in the contours. But here there's an easy way to decide. So if you take the black and white chessboard coloring, one of the two possibilities of the faces, then it's easy to see that each contour line has the property that it has all black faces on one side and all white faces on the other side. Which means that, so once you have this, you could say that, okay, if I cross a contour from the black side to the white side, then I have to increase my height. And if I cross it from the white to black, then I decrease my height. So this way you can, given the contours, there is one way to define, or two ways to define a height function. And this is exactly this height function. So, okay, so somehow there's a very nice correspondence. So basically the height function can be described by these two simple and independent simple random walks. Okay, and then the statement that so about the matchings.
So what you're telling in particular is if I flip both random walks, I get the same curves, but the heights will be inverted.
Maybe not, because there is this thing, the upper integer part. So maybe you get not the same curve, but the one that is left out. I'm not sure. Either you get the same or...
You do have the symmetry, right? Because if you... So what is the symmetry? If I have the same corner percolation curve, and I decide to move the black squares by 1 unit...
Yeah. Then you get just minus the height function.
So I just get minus the height function. But that seems not to be a symmetry.
Yes, because then you have to so
you point out due to the integer part.
yeah, so it's exactly the missing symmetry that makes sense. But I don't understand what's the problem.
So how does it work out? I mean, so if I exchange the black and the white squares on your chessboard, I keep the same curves, but I get a different height function, right? How?
Yes. So there is also that the 0, 0. So there is also one choice you have to make corresponding to that. So this what I have said works if the 0, 0 face is black.
Oh, I see.
Okay. Thanks. Okay, and so the statement, the combinatorial statement about the matchings translates to the simple random walks. I mean, that's why we did it.
Do you want to change the thing on this so that it doesn't go? Oh, I guess that kind of fits. Zoom out or zoom in. No, it doesn't really, because the bottom's not.
It does work.
Yeah. So go a little more and then.
Okay.
Yeah. Okay.
So the first time, technical development actually makes sense. No, I cannot change the.
Zoom back a little.
But why is it darker?
Yeah, that's what I'm asking. Oh, that looks pretty good. Just while I was there.
It's for some reason it's darker, isn't it?
Yeah.
Yes. Maybe put it physically closer or farther from the light source.
And then for the reflection somehow.
Okay.
I don't know if it's back. I think we can all still see, huh?
Okay. Okay. So the statement is that an up contour. So now we have up contours and down contours. Well, so once I haven't proved yet that there are only finite cycles, but if there are only finite cycles, then each cycle is either an up contour or a down contour, depending on black outside or black inside. I didn't see brightness. Okay. And so up contours. So okay.
It was pulsating.
Okay.
So it was.
Okay. So maybe I shouldn't move there. Doesn't matter. Okay. So if you have an up contour, you look at the smallest enclosing rectangle, you look at the marginals, and you see an up excursion here, and you see an up excursion there. And these two up excursions are compatible, by which I mean two things. They have the same height. That's the important one. By height, meaning the difference between the maximum and the minimum here and here are the same. And that's kind of the height of the heel in the up contour.
So you're saying that these two random walks are correlated?
No. So you have,
Yeah,
so the way
it
to,
didn't sound like they were, and yet you're saying the main difference is the same.
okay,
So
no, wherever you see, so this is an if and
I
only.
look at a contour, fine.
Yes, okay. And this is an if and only statement. So whenever you see a contour, if you look at the marginal, so if it is up contour, you see two up excursions of the same height. And wherever in the two marginals, if you find an up contour here of an up excursion here of height h and here an up excursion of height h, then the rectangle they give, there is a contour touching the four sides of the rectangle.
And if I found an up excursion here that was h minus 1 and here that was h, I wouldn't find a contour corresponding to that. I'd have to go out until I find
Yes.
one that is h
Yes,
and h.
yes.
And then there was
Yes. Yes, and there is some small compatibility condition that there is some parity issue. So the maximum in one of the maximum of one excursion plus the minimum of the other excursion has to be even. Okay, and down contours are down excursions. Okay, so we know where to find the cycles now. And so even without this information, showing that you have only finite cycles is not hard. So how do you find a finite cycle? So if in the, so there is this height function given by the sum of two independent simple random walks. If you find a box on the boundary of which the faces have all positive values, and find a bigger box on the boundary with all negative values of the height function, then there must be a zero level contour in between. So I claim that this happens actually with probability 1. So I take the origin, and so even on the zero level, so each contour has an associated height, which is, say, the height on its left side, whatever, black side. So even on the zero level, you have infinitely many. So I want to prove.
And it happens infrequently enough that there's still an infinite expected size.
Yes. Yes. Okay, and so how can you produce this positive box in the negative box in the height function? So take one of the simple random walks and look at the following events. So this is the trajectory of xn, the simple random walk. And you want to avoid this space-time barrier. So I mean that between time minus m and m, you have to stay strictly above minus square root of m. But at the two edges, at minus m and m, you have to be strictly above plus square root of m. And similarly here, you want to avoid this upper barrier. Okay, so by Brownian scaling, this has a positive uniform. Uniform meaning independent of m probability for simple random walk trajectory. And why is this good for us? So if both walks, so both xn, the horizontal, and ym, the vertical one, have this event, satisfy this event, then the sum of them, so for example on that, so this is this is the box labeled by mm, and this is 2m by 2m. So this 2m and this m. So for example on this edge of the box, what are the values? So since you sum up, so in the vertical one, you sum up from the values between minus m and plus m. And in the horizontal one, you are minus m. So at minus m, the horizontal one is bigger than square root of m. And in between, the vertical one is bigger than minus square root of m. So the sum is positive. So here along this edge, you get positive values. And I mean, around the whole boundary. And similarly, because of this barrier on the boundary here, you get negative values. So whenever you see this event in both walks, then you get a zero contour around the origin. And if you take this event indexed by little m, and also by some capital M, a much bigger m, capital M, then these two events are almost independent. So, and they have a positive uniform probability, so they happen infinitely often. Okay, and that's it. So the proof for the finiteness. So once you know the correspondence, it's not difficult. Okay, but we know much more about the cycles, so we know how to find them. These are these products. So these are some. So you have two simple random walk excursions, and the cycle is somehow a strange combinatorial product of them. And so there is a combinatorial description how to get exactly the cycle, which is kind of difficult. I won't, but it's nice. I won't go to that. But anyway, you have some hope to do more with this description. And so there are two natural critical exponents you can try to look at. One is, okay, I haven't showed that the expectation of that these cycles are big, but that can be easily done. But there is a much better result, so the tail probability. So what is the probability that the diameter of the cycle of the origin is bigger than some n? So that decays to 0, probably as with some power law. And you can also look at so given that you have a big cycle, so the diameter is n, how wiggly the cycle is. So what is the actual length of the cycle? So expectation of that. So that's hopefully some n to the delta, where delta is obviously between 1 and 2. Clear? Right? Okay, and I say that these actually two things do exist and can be computed, and so gamma is this number, and delta is this number. So
Where the hell just square root of 17 from me?
yeah, I will. Okay, so this means that these curves are square root of 17 plus 1 over 4 dimensional. So, like Mandelbrot saw that, that's 4/3. So now you see this is square root of 17 plus 1 over 4. Okay, and the sum of these two numbers is 3/2. And this is not an accident, but it's because, so if you take, additive Brownian motion is when you take a horizontal Brownian motion and a vertical Brownian motion independent, and you just sum of them. So this is a height function. This is the scaling limit of our height function. And if you take a slice, it's a level set that has Hausdorff dimension 3/2, which is, discretely, so that's the 3/2. And so discretely it means that if you take an n by n box, then you have, so each walk has square root of n fluctuations. So you have square root of n heights, and typically they have the same, altogether you have n squared territory, and each slice typically have the same size, so each slice should have n to the 3/2 points on it. So that's a discrete analog of dimension 3/2. Okay. Okay, so the way I did it, so I computed delta, I proved that the sum is 3/2, and I subtracted 3/2 from delta from 3/2. So it also kind of means that I haven't seen my. Okay, there is. So this is this picture is not very visible, but visible a little bit. So this is the set of contours on a fixed height. So this darker thing is one cycle, and everything else are other things. So you can. So what I say is that the whole set is basically 3/2 dimensional, but these cycles have some smaller, the square root of 17 plus 1 over 4, so 1.28. So you have this cloud of smaller things attached to the big cycles, and altogether they add up to this 3/2. Okay, so I want to show how this square root of 17 arises. So first of all, instead of, okay, so once again the statement is that the expected length of a cycle given that the diameter is n. So instead of this, there is a more natural parameter, which is, we know that each cycle is given by two independent simple random walks of the same height. So let's take two simple random walk excursions of a fixed height h. So this is this curly E sub h. So take two excursions. Okay. So this is curly E of h. Is a simple random walk excursion conditioned on having height h. So the length of that is very close. It's kind of h squared. So this has a non-trivial limiting distribution with this a mistake. So not Gaussian tails, but exponential. Well, depending in this h, it's exponential. Tails. So instead of conditioning on the diameter being n, I condition on the height being h, which is kind of the same thing as conditioning the diameter being h squared. So this L of h is the expected length of the contour given by two excursions of height h, and that should be h to 2 delta. So I want to find this delta. Okay, so what is an excursion of height h? You just run simple random walk conditioned to hit h before hitting 0. This is the der leg of the walk, and then from h you run it backwards, conditioned on hitting 0 before h plus 1. And the point, so this is a simple random walk excursion, and the important thing is that so the der leg is a Markov chain and the back leg is a Markov chain, and the transition probabilities between from I to I plus 1 doesn't depend on h. So if you look whenever in between, what you see is you don't see what the conditioning on h was. And that's a very important compatibility property to do any computations. Okay. Okay, so now, so take two simple random walk excursions, say one is from height, so both are of height h. So say one is from height 0 to height h, and the other is one from height minus h to 0. So two up excursions of height h. This way, the cycle I get will have the value of the height function is 0 along the outer side and 1 in the inside. Because here you see this is, I add up this h to this 0. Okay, so if I look at the 0 and the 1 values of the height function in this box, in this rectangle, then I basically should see the cycles on the 0 level. So between zeros and ones. But of course, the total number of zeros and ones in here is much more than this. So it's h squared, the same way as the 3/2 came, multiplied by 2. Okay, so there are certainly much more zeros and ones than just the ones around this cycle. So fortunately, so that's a lamp. Okay, so one point is this perimeter lemma, which just says that, well, it's actually enough to count. So if you want the length of the cycle, it's enough to count how many zeros and ones are around. That's not very surprising. So we could get somewhere by counting zeros and ones. And the other is this Versailles lemma, because I think it looks somehow like a Rococo French park. So the layout of the park. So there is some, if you look at the contours on the same level, there is some restriction how they can fit together. So the enclosing boxes, they cannot have overlapping marginals. That's the point. So I hope you see what I mean by that. For example, so one important thing is that here you cannot have, so a cycle like this, that on the same zero level, that comes in, that intersects the box but doesn't contain in the box, there is no such thing. So that's very good. But you still can have many, so all cycles on the zero level are contained in the box. But, okay, which means that they are given by sub-excursions. Of the same height. Okay. Moreover, because of the compatibility condition I was telling you in the simple random walk excursions, like conditioned on their existence, the shape is just like a contour given by two independent simple random walk excursions of some smaller height. Okay, which means that if I find the number of these things inside for all possible sizes, and I subtract that from the overall number of zeros and ones, so the overall size of the level set, then I get this one big, the size of that one big thing. Okay, I was lying a little bit, but never mind. Eventually you get recursion. So L of H is that what we are looking for. So the expected length.
I'm not sure that we're all going to be able to follow.
Yeah, I won't. Yeah, I will. So the point is, so you get a recursion. So for this L of H thing, you get, so this R of H is something known, the total overall number, so something H cubed. And you have to subtract all the smaller ones with some kernel. Okay, so this is a linear recursion, but with, I mean, all the previous ones play a role. Okay, so this looks like, and you want to find the growth rate of L. So this looks like an integral Volterra equation of the second kind. Okay, so like this. So you have something known and integral kernel. Okay, except, so I'm sure you skipped this thing, but this is actually important. So these numbers like 4 over 15 and 4 over 3 and this H cube over M quarters and all this, for the exact form of the kernel really matters. So there is this stuff here, and there is the stuff you think that, oh, that's really smaller order. Okay, so if you cut off all that looks like junk, and you just, instead of the discrete thing, you look at the continuous version, so replace sum by integral sign, then you get an equation that, so if you differentiate this 6 times, then you get an OD, which although it's not with constant coefficients, but it can, so it's an Euler type OD, it can be solved. And the growth rate of, so you get a 6th order polynomial, which fortunately it has obvious symmetry, so it breaks up, and it has these roots, square root of 17, blah blah. Yeah, so that thing. So the general solution of that OD looks like this. And well, you might think that, okay, so I know that the general solution, if C1 is not positive, is not 0, then this the solution grows like that. So the discrete thing also should grow like that. Mm-hmm. Okay. So the discrete thing also should grow like that. However, there's a big, so for a while I was trying to, okay, the discrete should be close to the continuous one, even with these errors. But for example, if you do exactly the same coefficients, but discrete and continuous, then the C1 will be different. So there is no hope to show that actually the two solutions stay close. So it's not just a perturbation thing, but there is some more substantial. So what you have to actually do is this usual thing. So you take the generating function of the sequence. I switched between k and l, but don't worry. And so since these have some polynomial growth, this blows up at 1, so has radius of convergence 1. So you turn the recursion I gave to an ODE for this generating function, which is a horrible thing because like Maple and Mathematica is just not good enough to do it. So you have to do it by hand. So it's a singular ODE, and you get, there is some analysis you have to do, and it turns out that you can read off you cannot solve the ODE explicitly anymore, but you can read off the size of the singularity at 1. And from the size of the singularity at 1, you can, by Tauberian theory, you can read off the growth rate of the coefficients, provided you have something which is like they are monotone, which is true. You can prove that with the coupling. And then you get, actually, from this ODE, you get the growth rate of the things which you wanted. Okay, so that's the end of the proof. There are many like interesting things about it. So, I mean, like open problems and stuff. So one is that, so after I did it, I was told that Dalang and Montfort and Walsh, they have, in the past 20 years, they have been working on this, which I didn't know. So on the level sets of additive Brownian motion and fine geometric properties of the level sets of additive Brownian motion. And for example, they wrote a big paper on showing that there is a unique Jordan curve in the boundary of Brownian bubble. So there are big Jordan curves in this level set, but it's merely the existence. So obviously, what we now conjecture that the dimension of that Jordan curve is our dimension. And they actually had some interesting, some funny. So the dimension of the whole boundary of this thing with all the mass around it, that has something smaller than 3/2, and they have some number there. So that's a obvious thing to do to prove that the scaling limit of the big cycles is this Jordan curve they have. And there are many other, so one interesting thing is that, so there is this height function, the additive Brownian motion, and if you do the normal domino tiling thing, then the height function is Gaussian free field, which is a conformal invariant random height function. And there is an obvious interpolation between the two models, namely that you take some small probability you have some errors in the all vertical or all horizontal things. And in this way you get so there is a way to get from Gaussian free field to additive Brownian motion and in between and whatever. Thank you.
So this way of interpolating between the Gaussian free field and additive Brownian motion, it seems like in the scaling limit it should just be the average. So lambda times 1 plus 1 minus lambda times the other. Is that correct?
Yeah. So somehow, so one is like, so it's like you have Gaussian free field, you stretch it or push it. I don't know, push it in one direction horizontally, and you take another copy, you push it in the vertical direction, and then you add up these two things. So that's the height function in the in the interpolating model, or subtract whatever. Yeah. And then what the statement is that as this pushing becomes more than going to infinity, the sum goes to additive Brownian motion, or it doesn't.